So now let's take a look at an example problem 6.4.1 where we're working with an op-amp multiplier. So in this problem here, they ask us to determine the relation between the input voltage VI and the output voltage VO of the op-amp circuit that we see in the figure below. We want to assume that the op-amp has the following properties. One, we're going to assume that the op-amp gain G is very large. We're going to assume that VO is equal to negative G V sub I, and we're going to assume that the op-amp input impedance is very large. Therefore, the current I3 that's drawn by the op-amp is going to be very small. So the terminology for very large and very small is going to become important, and we'll see that as we're going through the solution to the problem. So down below we have our diagrams here of the op-amp circuit, A and B. We'll redraw A and go through that in our solution, and we'll talk about how we can make the assumption to get our open circuit over here for B. So now that we've had the opportunity to read through that problem statement and understand what they're giving us and what they're asking us to solve for, and take a look through our given diagrams, the next step is to create our setup page here. So for our setup page here, we're dealing with an op-amp multiplier. They give us three assumptions in this. First, that the op-amp gain G is very large. They tell us that V out is equal to negative G times our V in. And the op-amp impedance is very large, so therefore our I3 is very small. So they want us to find the relationship between VI and VO. So I redraw out my diagram down here. I have my voltage source, my VI right here. I have my resistance Ri here, my current I1 there, I2 and I3 going into our amplifier there with our gain G right there. We have our RF up here, I have our V out over here. We have our ground right there, and there's our voltage V1 there. So because the current at I3 drawn by the op-amp is very small, and given to us in the problem statement, the input terminal pair can be represented as an open circuit. So that's going to simplify things down. So we can redraw this now by this diagram they gave us here in our open circuit. So we have our VI over here. Now we have our RI, I1, I2, and I3, my RF over here. And down over here we have our gain here. It's a voltage negative GV1. Here's our VO over here and our V1 right there. So let's go through this piece by piece. Let's just deal with our resistance over here for our first one, our initial here, which is R1. So our resistance for over here, we have our V is equal to IR, general equation. So what are our V's coming into this guy here? Well, there's our VI right there, and there's our V1 over here. So therefore, we have that VI minus V1 is equal to I1 R1 right there. So we can rearrange that, solve that for I1. I1 is equal to VI minus V1 over R. So now we do the same thing over here for our RF, for our second resistance, R2 over here. So we have this resistor here, current here, have our voltage source of V1 right here, and we have our other voltage source, V0 over here. So we plug that into our V equals IR, so we have our V's of V1 minus V0, our V1 minus our V0 for this guy here, is equal to our I2 R2. Here's our I2 R2 right there. So therefore, we rearrange, solve for I2. I2 is equal to V1 minus V out over our R2. So from here, there's no capacitance, so therefore we can use our conservation of charge. Conservation of charge will give us for our particular problem that I1 is equal to I2 plus I3. However, the op-amp impedance is very large, so our I3 is very small. So like I said at the beginning of this problem, very small, very large are keywords here. So from the given information, with that being very small, we'll say that that goes to 0. So our I3 is approximately equal to 0. So we can plug that into our equation up here for our I3 right there, put that to 0. So when we do that, we end up with our I1 is approximately equal to I2 plus 0 when we plug that in there. So therefore, I1 is approximately equal to our I2 based upon that fact that our op-amp impedance is very large, so therefore our I3 is very small, or 0. So with that there, we can go back now to our equations for I1 and I2, And now that we see that I1 is approximately equal to I2, we can set these two guys equal to each other. And we do that, we end up with VI minus V1 over our R1 here is equal to V1 minus V out over our R2 here. So our last piece of information that was given in the problem statement here, we had the fact that our V1 right here is equal to a negative V out over G. So we can plug that down in for our V1 right there from our previous equation on the previous slide. So this now becomes, when we plug in negative V out over G, and for V1, we end up with this relationship here that we now have V1 minus a negative V naught over G all over R1 is equal to, when we plug in for V1 here, we have a negative V naught over G minus our V naught right there all over R2. So now we can rearrange and simplify this a little bit, and we do that there. What we end up with is this relationship here, that we have V1 over R1 plus V out over R1G is equal to negative V out over R2G minus V out over R2. So back to our givens, the fact that we have G being very large. So if we have a very large term in our denominator, the denominator is therefore going to make that fraction very small. By very small, I mean we're eliminating that. Large, very large, going to infinity, makes this go to 0, makes this go to 0, right there and right there, which reduces down and simplifies to this relationship here, where I now have my V1 over R1 is equal to negative V out over R2. So we can rearrange that and solve for our V out, and we do that. Our V out is equal to a negative R2 over R1 times Vn.